Greetings grade 11s and grade 12s, and welcome to Butu Academy, lessons that empower. And today we are going to be looking at Newton's laws and applications of Newton's laws. This is the second lesson on this particular topic. We did have a first lesson where we looked at the different kinds of forces, and I'd really recommend those who did not watch the first lesson to do so that this lesson will also make sense. All right, I did indicate in the previous lesson that in today's lesson we are going to be looking at the drawing of force diagrams together with free body diagrams, and I also emphasized the importance of being able to draw a free body diagram in particular, because it also appears in other parts of physical sciences paper 1 other than Newton's laws. It's a skill that you're also going to need in topics such as work, energy and power, those who are in grade 12, together with electrostatics as well. These are some of the things that you will be using in other topics as well. So it is very important that you really master this skill of drawing a free body diagram in particular. Now let's get straight into the two diagrams. Now the first one that we're going to look at is what is referred to as the force diagram. Okay, now a force diagram is a drawing of an object and all the forces acting on it represented by arrows. Now in a force diagram, what you do is that you draw the diagram representing the object. In other words, if it's a car, you draw the car, or you draw a box if it is a box that you are looking at. If your object of interest is a car, then you draw a car. If your object of interest is a tree, then you draw a tree, and then you represent all the forces acting on the tree or the car or the box with arrows. Right? Now the direction of the arrow will indicate the direction of the force, and the length of the arrow will indicate the magnitude of the force. So it is important again to also look at the relationship between the magnitudes of the forces. Make sure that you draw a short arrow for the smaller forces, and also draw a longer arrow for the bigger forces, or the forces that have a larger or bigger magnitude. Okay, so if you have two forces, one of 30 newtons and another one of 10 newtons, the arrow representing the 30 newtons force must be longer than the arrow representing the 10 newtons force. That is also important. Let's look at a practical example on how to draw a force diagram. Now here you have a 10 kilogram box placed on a table. A horizontal force of 32 newtons is applied to the box, and it causes the box to slide to the left. So we therefore expect that this is a force that is applied on the left hand side, because it is pulling this object to the left, and it causes the object to move to the left. And also there is a frictional force here which is exerted by the surface. We know that based from the previous lesson. And this is an object that is in contact with the surface and is sliding to the left. Okay, what are we expected to do? We are expected to draw a force diagram representing all the forces acting on this box. Like I said, in our answering of this question, we are going to draw the object. Okay, so we are still going to draw the 10 kilogram box. There is our box, and then we are going to indicate all the forces acting on this box using arrows. Now the first one is the most obvious one. It's the one that already appears on the diagram that we have here, and that is a force going to the left. Okay, there's our force. Okay, let me fix that. That's a force going to the left, and that is the applied force, or you can just write capital letter F. All right, and we know this is a 10 kilogram block. It's an object of mass. Okay, the weight of the object must also be indicated here, because it's also one of the forces acting on the object. Now the weight must be drawn from the center of the box, because the weight is distributed across the whole body of the box, but we are going to study it at the center. So the center of mass of the box is right at the center of the box. Therefore this is our weight, or the force of gravity. Now what do we know? The two forces that are there because of the fact that the box is in contact with a surface. The first one is the frictional force. Okay, we are told that there is a frictional force of 7 newtons. But remember, now we have a 7 newtons and a 32 newtons acting along the same line. So I must indicate that the frictional force is actually smaller than the applied force. And this frictional force is a kinetic frictional force, because this is a box that is sliding to the left. Therefore, the frictional force must slide to the right, must point to the right, because the frictional force must oppose the direction of motion. Okay, and look at the position of where I drew the frictional force. I drew it right on the surface, because this is a force that is coming from the surface. Okay, unlike the weight must be applied on the object at the center of the object. And then the applied force, I drew it from where it's coming from. If this is a pulling force, it's in the object that is applying this force is in contact with the box from the left hand side. Unless it was being pushed, then it would be coming from the right. In this case, it's being pulled to the left. Okay, the last force that we are going to draw is what we refer to as the normal force. We spoke about this. It must also come from the surface. There is our normal force. Again, look, it starts from the surface because it comes from the surface and it's applied on the box. Okay, this is what a force diagram actually looks like. It's not one of the force diagrams that we're going to see a lot in your assessments, because we spend most of our time drawing the free body diagram, but it is also important because it appears in the exam guideline and the CAPS document as well. So it is very important that we know how to draw the force diagrams. Okay, then we move to the most important one, which is the one that I kept on emphasizing, and I'll keep on emphasizing that you master the skill of drawing this particular diagram. Otherwise, it becomes a problem for you to solve other problems involving forces. You must be able to draw the free body diagram. Right, now what is a free body diagram? So in a free body diagram, we represent the object of interest using a dot. Okay, so in our lesson, we're going to use a dot to represent the object. So if it's a car, it's a person, it's a tree, it can be anything. Even if it's a planet, we're going to use a dot to represent whatever object that we are looking at, and all the forces acting on it are going to be represented by arrows. So in a free body diagram, you therefore expect a dot and arrows. Okay, so the dot represents the object of interest, and then the arrows will represent the forces. Each arrow points in the direction of the force it represents. Of course, if it's a weight, it will be an arrow pointing downwards, because the weight is always downwards. If it's a force representing, if it's an arrow representing a force applied and the force is applied in the right direction, therefore the arrow must point to the right, because that is the direction of the force. The forces must be drawn as arrows starting from the dot and pointing away towards the direction of the force. Okay, so you draw the dot first, then you start drawing the various forces using arrows pointing in the direction of the force. If the force is upwards, you draw an arrow pointing upwards. If the force is to the right, you draw an arrow pointing to the right. But the arrow must start, very important, the arrow has to start on the dot. Okay, the arrow has to start on the dot, and it must point away from the dot in the direction of the force. Now let's use the very same example that we did with the force diagram, but now we are going to use that same example to draw a free body diagram. Okay, it's still the same force, it's still the same box on a table. There's an applied force of 32 newtons, and there's a frictional force of 7 newtons, and so on. So in this case, we are asked to draw a free body diagram showing all the forces acting on the box. Okay, so to draw a free body diagram, remember, what did we say? We are no longer going to draw the box. We are now going to use a dot to represent the box. So here's my dot here, which represents the object of interest. The object of interest, remember, is the box. Okay, again, the most obvious force, it's still the one that we see on the diagram, and that is the force to the left, and that is the applied force. Okay, and then again, because this is a box of mass 10 kilograms, we therefore expect that this will also experience a weight or a force of gravity pointing downwards. And the two forces coming from the surface, the first one we spoke about in the previous slide was the frictional force. There's our frictional force, kinetic friction. And lastly, we have our normal force. This is the normal force. And this is what a free body diagram generally looks like. The dot at the center represents the object of interest, and the various arrows that you see around the dot are the forces that are acting on that particular object. So in this case, this is an object that is experiencing 4 forces in various directions. Okay, now in the next slide, what I want us to look at is strategies that you should apply when you draw the various forces, because so far we've only used examples, but you need to have an understanding of how to draw each and every force when you are required to do so. And how to draw each and every force is important because you have to draw it correctly, otherwise it becomes a problem when you are solving other questions regarding that situation that you are looking at. For instance, if you have a wrong free body diagram, it becomes impossible to solve the mathematical problems that are to follow from that particular problem. Now, let's start with the frictional force. The frictional force, we all know, comes from the surface, and it has a relationship with the surface. What do we know? Each time the frictional force must be parallel to the surface. Okay, here I'm going to use a broken line to represent the surface. Just to remind you, as you see there, I emphasize the word parallel because the frictional force must always be parallel to the surface. So let us say this is the surface and there's an object on the surface. Okay, if this is an object that is moving, let's say to the left, like the previous 2 examples that we had, the frictional force must be an arrow parallel to the surface and pointing in the opposite direction. Okay, here what I want to emphasize is the fact that the frictional force must always be parallel to the surface. Okay, so this is a horizontal surface. It therefore means the frictional force must be a horizontal force because it has to be parallel to the surface. But it also happens sometimes that the surface is not horizontal. The surface is a slope, or what we sometimes call an incline. That is, there is an angle between the surface and the horizontal line. A surface like this one. If you look at this surface, you can see this is not a horizontal surface, because if this is your horizontal line, there will be an angle here between the surface and the horizontal line. Therefore, this is an inclined surface. On an inclined surface, we also have to remember it does not change the fact that the frictional force must be parallel to the surface at all times. So our frictional force again is going to be drawn parallel to the surface. As you can see, this is an example of an object that is moving down the slope or down the surface. So if this surface represents a slope, and therefore this is a frictional force going up the slope to show that the surface, the object is actually going down the slope, because the frictional force must always oppose the direction of motion. Let's then move to the normal force. Okay, the normal force, we all know that it must be drawn perpendicular to the surface. Again, the surface plays a role here. Perpendicular to the surface, meaning that the angle between the surface and the normal force must always be 90 degrees. This is a force which is commonly misunderstood, or very often learners make a mistake when it comes to the drawing of this particular force, because sometimes they'll draw it facing in the wrong direction, because they don't understand that the force must be drawn perpendicular to the surface at all times, regardless of the orientation of the surface. If the surface is horizontal, then the normal force must be drawn vertical. But then this becomes a challenge when the surface is an inclined surface or a slope. Now this one is quite easy, I would assume, for most of you, because we know if the object is sitting on a horizontal surface, we expect the normal force to be perpendicular to the surface. In other words, there has to be an angle of 90 degrees between the surface and the force. The normal force and the surface, they have to be perpendicular to each other, which means the angle between the two must be 90 degrees at all times. This one is not really much of a tricky one. The tricky situation happens when the surface is now no longer a horizontal line. It's now an inclined surface or a slope. Again, if you have an object sitting on an inclined surface, meaning there's an angle between the surface and the horizontal lines of your book. In this case, if you look at this one, again, the normal force has to be drawn perpendicular to the surface. If you can look at these two normal forces, you can see the direction is not the same, because the direction of the slope is also, the orientation of the slope is also different. Okay, the most important thing is the weight perpendicular. Okay, at all times the normal force together with the surface must be perpendicular to each other. In other words, there has to be a 90-degree angle between the normal force and the surface at all times. It does not matter what the surface looks like, or if the surface is horizontal or it's an incline. All right, again we have the surface now still an incline, but now facing the other direction. The normal force must always be perpendicular to the surface. Again, the angle between the normal force and the surface must be 90 degrees at all times, regardless of the orientation of the surface. So make sure that you get the normal force correct. That is the most challenging one for many learners that we've seen when marking various scripts, both grade 11 and grade 12. So make sure that your free body diagram has the correct normal force, and it must be perpendicular to the surface at all times. All right, now let's look at the weight. Again, this is a force which has to be understood when we draw the free body diagram. We don't really have a problem when the surface is a horizontal surface. Most of the time, learners know that the weight or the force of gravity has to be drawn as a line pointing downwards. But this has to be the case at all times, regardless of the orientation of the slope or the orientation of the surface. Again, if the surface is an inclined one or a slope, the weight still has to be drawn pointing downwards at all times. It does not matter, regardless of the orientation. Now, here, what you have to make as your point of reference are the lines of your book. The weight must be perpendicular to the lines of your book, or if you can't remember that, just remember that the weight must be drawn as a line that is pointing towards the bottom of your book or the bottom of your script if it's a script. Okay, as you can see, this is a weight pointing towards the bottom of my script, as you can see. Again, regardless of the orientation of the surface, the weight at all times is pointing towards the bottom of the script or the bottom of your book if you are writing in a book. Or just the other way to remember is that the weight is perpendicular to the horizontal lines of your book. The lines that you write on in the script or in the book must be perpendicular to the weight, as you can see. That's our weight, and therefore the direction has to point perpendicular to the lines of the book, or downwards or towards the bottom of your book, which is downwards again. Now, these are some of the strategies that you have to remember each time you draw a free body diagram. The frictional force is related to the surface in terms of direction. It's parallel to the surface. The normal force perpendicular to the surface at all times. I have seen, if I may just go back, especially in situations like this one. Let's pay attention to this one. Learners would find that they know that the surface is an inclined surface, but they'll still draw a normal force pointing in that direction as if it's this one. And we do not do that. As you can see, the angle between the surface, this particular surface, and the normal force there is not 90 degrees. So make sure that you at least try to show the marker or the examiner that you know that the angle between the normal force and the normal force, let me just quickly remove this. We have a slight challenge here. Okay, so the normal force must always be perpendicular to the surface. Okay, right. Now let's move at some worked examples here. In our worked examples, what we are going to be looking at is various situations where you have to draw a free body diagram. Now, this one I consider it to be an easier one. Now, we are going to, for all of these situations, we are going to draw a free body diagram. So here we have a 50 kilogram block pulled to the right by a force F. We can already see the force F. Okay, as we can see, this is an object that is in contact with a surface. Let us assume, unfortunately in this case, the information is incomplete because it has to be clear whether the surface is smooth or rough. Let us assume this is the broken line. The broken line, as you can see, let's assume this is a rough surface. Okay, and this is a rough surface. If this is a rough surface, we expect that this object will experience a frictional force if it's sliding to the right. In this case, the box is pulled to the right. So how do we draw a free body diagram for this one? In our free body diagram, we have to think about the fact that a free body diagram is represented by a dot, which represents the object, and arrows, which represent the forces. The first force that I'm going to draw, because this is a 50 kilogram block, is the weight, to show that this is a force of gravity, or you can write the letter W to indicate that this is the weight. The second one is the obvious one, which I see there, the force applied, which is F. The third and the fourth one would be the forces that are coming from the surface. The first one would be the normal force. As we can see, this is a horizontal surface, therefore the normal force must be perpendicular to the surface, and therefore it must be a vertical force. Okay, and lastly, if this is a box that is moving to the right, there will be a frictional force. If this is a box that is moving, this would be Fk. If it's not moving, that would be Fs. In this case, let's make the assumption that this is a moving object. Okay, it's pulled to the right. So if it's pulled to the right, let's assume it's moving to the right, because it's also possible for an object to be pulled to the right but not move. That is, if your force that is being applied here is not greater than the maximum static friction. We spoke about that in the previous lesson. You should try and revise that if you forgot it. Okay, now let's move to the second object. Now again, we still have a 50 kilogram block pulled across a rough surface by a force acting at an angle. This one has complete information. In this case, we know that the surface AB is rough, therefore there will be a frictional force. Now, it is extremely important to note the direction of our applied force. Okay, we are going to start with that. As we can see, our applied force is applied at an angle, so we can't draw a horizontal force like we did in the previous diagram above. In this case, we are now going to draw a force pointing in that direction, making an angle of 20 degrees with the horizontal. We are not really going to draw it to scale, because if you are to draw it to scale, you're going to need other instruments such as a protractor to do that. Okay, so this is a force this is an arrow representing the applied force. What else do we know? We know that this is an object that is pulled across, and it's also on top of a surface. Okay, because it's on top of a surface. But before that, we know that this is a 50 kilogram block, therefore it has mass. If it has mass, it must also have force of gravity, or the weight. And because it's on a surface, it must also experience the normal force, which is perpendicular to the surface at all times. The surface is still horizontal. What is acting at an angle here is the force. So you must be able to differentiate or distinguish between a force acting at an angle, or when the surface is at an angle, where we call it a slope. Those are two different scenarios. Even the application of your mathematical calculations become different based on each scenario. Okay, the other thing that we need to remember, this is a rough surface. If this is a rough surface, it means there is a frictional force. We are going to have our frictional force. This is assuming that this is an object moving to the right. Okay, right, now let's move to another example, two more examples before we wrap up the lesson. Now in this case, let me just go back a little bit. Okay, let me just go back a little bit. Look at this one. This is a 50 kilogram block which is on a horizontal surface. It is experiencing an applied force that is applied at an angle. It differs from what is happening this side. What is happening here is that the object itself is on top of an inclined surface. Okay, this one becomes a little bit tricky, and this is where we see the most mistakes by learners are coming usually from this type of free body diagrams. What I usually say to learners is that if you do not want to mess up your free body diagram here, the most important thing that you need to do, first draw the surface before you draw the free body diagram. What I mean by that is that, let me use a different color. Okay, I'll try to get a different color here. Okay, I can't find a different color. Okay, let me try to, okay, yeah, let's use a different color. I'm going to use this blue broken line to represent the surface. Okay, it's not so much like the one that we have here. I'm going to use this broken line to represent the surface. Okay, if this is the surface, then I'm going to change the color to red again. This is the color that we're going to use to draw the free body diagram. If the blue broken line represents your surface, the object will be on top of the surface like it is in this case. Now, first things first, I would advise you, it's not a must, it's not, you are not compelled to do this, but I would advise you to draw the weight or the force of gravity first, so that you have your forces in perspective. What do we know? The force of gravity must always point towards, the force of gravity must always point towards the bottom of your book. Okay, there is your force of gravity. The blue line is just the surface. Please do not put arrows on the blue line. The blue line is not a force, because the moment you put arrows on the blue line, which is the surface, then it becomes as if you have drawn extra forces, then you start losing marks there. The reason why I drew that blue line is so that I can have a proper drawing of my normal force, especially together with the other forces that are related to the surface. We know the frictional force together with the normal force are related to the surface. So if I can see the surface, then I'll draw forces correctly. Secondly, this object is in contact with the surface. If it's in contact with the surface, there must be a normal force. There must be a normal force in this direction. As you can see, our normal force must be perpendicular to the surface. Do you see that? This is the reason why we need our surface before we can draw. Of course, there are those who will not struggle to draw this even without drawing the surface. They'll still get it correct. Here we are helping those who are struggling, especially with the normal force. Okay, now this is a block which is pulled up a rough incline. In other words, while it's being pulled up, let's start drawing first the force that is applied, our F here, which was actually the most obvious one. As we can see, it is parallel to the incline, or to the slope. It's parallel to the slope. So if when we draw it again, it has to be parallel to this incline there. That's the applied force. Then we have to remember this is a rough surface, which means there is a frictional force. If this block is being pulled up the slope, therefore there has to be a frictional force that is down the slope. Now in this case, our frictional force will be pointing in this direction, and if this is a force, if it's an object that is moving, therefore the object will experience a kinetic frictional force. Okay, so this is a free body diagram of an object on an incline, and I'd really recommend that you practice this one a lot more than the others, because this is where we see the most mistakes. Right, so as you can see, the blue line there, like I said earlier on, was there to guide you, especially with the drawing of the frictional force together with the normal force, because those are the forces that are related to the surface. They are either parallel to the surface, which is your frictional force, or perpendicular to the surface, which is your normal force. Right. Lastly, we're going to look at a mass block which is hanging down a pulley by a rope. Again, as soon as you see the word rope, you know the type of force that we're going to experience there is the one that we did last in the previous lesson, and that is tension. Okay, this is an easy one. Again, it's another one where we commonly get mistakes here. Mistake number one: let us assume that there is a normal force here. There is no normal force in this one, because this object, this mass block here, is not in contact with any surface. Okay, again, we are going to say the mass block is going to be represented by a dot, because we are drawing a free body diagram. Right, as we can see, this is a block of mass, therefore it has to experience a force of gravity or the weight. As you can see, the weight, regardless of the orientation of the surface or how the weight is held up, how the mass is held up, the weight must always point downwards or towards the bottom of your book or perpendicular to the lines of your book. Right. Then there is tension. What is keeping this mass block up there is a force which is pulling it up. Therefore, the force that is pulling it up is this one, and that is what we call tension. Of course, sometimes some people would prefer writing FT for tension. I'll just write the letter T for tension. This object experiences only two forces. I would like to emphasize again, this mass block does not have a normal force. Unlike with all the other three examples that we've done so far, if you look at the previous example that we did, so in this case, this object was on a surface, this one was also on a surface. Both of them would obviously have to experience a normal force. This one is also on a surface, the 100 kilogram block is also on a surface, but this one is not on a surface. It's not in contact with any surface, therefore there is no normal force, and this is the only one of the four that did not experience any normal force. I hope you have a better understanding of the drawing of force diagrams together with free body diagrams. Like I did indicate last time around, together with now, that it is very important that you master the drawing of the free body diagram. It will help you a lot with your calculations, especially once you've started doing the laws, first law, second law, and so on. Right. I hope that you've been empowered by today's lesson and you have a better understanding. We meet again on the third lesson on Newton's laws and applications of Newton's laws. In the third lesson, we're going to be looking at the components of the weight. How do we draw them on a free body diagram, and how do we calculate them? Just because this is a topic that is that comes after the vectors in 2 dimensions. Just revise how you resolved a vector into its components, because that's the skill that you are going to apply in the next lesson. So that's what we're going to be doing next. Don't miss out on that one. In the meantime, go through the video as many times as possible until you have a proper understanding, and do as many practice questions as possible. We meet again in the next lesson. Thank you so much. This has been Mbuto Academy, Lessons that Empower.